usually when we think about time travel, um, there's this expectation of a machine, you know?
Oh,
You
absolutely.
picture a DeLorean with glowing circuits or like some massive spinning metallic gyroscope in a secret government underground lab somewhere.
Right, yeah, like it's an engineering process.
Exactly. You punch in a date on a keypad, pull a heavy lever, and boom, you are in the future. It feels very mechanical.
It does. It feels like something we just haven't figured out how to build yet.
Right. But when you step into the world of advanced astrophysics and quantum mechanics, that mechanical sci-fi time machine seems almost quaint.
Yeah, it really does.
Because we are looking at a cosmic landscape where time travel isn't something you build in a lab. It is something that is already out there, naturally occurring, just waiting in the dark.
I mean, it sounds like pure science fiction, but this premise is rooted in some of the most rigorous physics we have.
Yeah.
We aren't dealing with hypotheticals here. We are dealing with the actual mechanics of the universe.
And that is exactly what we are getting into. Welcome to a brand new deep dive. Today, we are pulling from notes and discussions based on the Deep Space Channel Ziko's space stories, and specifically exploring the recent breakthroughs and theories of the world-renowned physicist Professor Brian Cox.
Such a fascinating topic.
It really is. And our mission for this deep dive is to completely upend the way you look at the night sky. We are taking the common idea of black holes, that they are just massive cosmic vacuum cleaners, and we are throwing it out the window.
Thank goodness, because that myth really needs to go.
Right. According to the advanced physics that Professor Cox outlines, these objects are not vacuums. They are nature's ultimate time machines.
And, Professor Cox has this really unique ability to take the most complex, arguably terrifying secrets of the cosmos and reveal the underlying elegance of the physics.
He really makes it sound like magic.
He does. But to really grasp what he's proposing, we have to start by tearing down that vacuum cleaner myth. Black holes don't just roam around sucking things up.
Right, they aren't malicious.
Exactly. The fundamental shift in thinking requires us to look not at how they interact with matter, but how they interact with time itself. Get comfortable, because this challenges everything we know about reality.
So let's get right into the mechanism of that, because you and I, and everyone listening to this right now, we experience time as a rigid progression.
Yes, a straight line.
Right, it ticks away second by second on our watches. It feels completely immutable. But the fundamental principle here, according to Cox, is that time is a physical dimension interwoven with space, creating space-time. And it is entirely flexible.
Yeah, and to understand why time is flexible, we have to look at the geometry of the universe.
Yeah.
We often hear that tired old metaphor of, like, a heavy bowling ball sitting on a stretchy elastic mattress.
Oh, yeah. Every high school physics class uses that one.
Yeah.
To show how mass bends space-time.
Right, and it's fine for basic gravity, but for a black hole, a better way to visualize the mechanism is to imagine space-time not as a static fabric, but as a rushing, flowing river.
Okay, I like that. A river of space and time.
Yes. Out here in deep space, far away from any stars, the river is wide and moving incredibly slowly. But when you place a massive object in that river, like a star, a waterfall begins to form.
Oh, wow.
The water space-time itself flows faster and faster toward the object. Now, take a black hole.
Which is unimaginably heavy.
Exactly. A black hole contains the mass of millions of suns crushed down to an infinitely tiny point, the singularity.
Right.
The gravitational pull is so intense that the waterfall it creates is unimaginably steep. As space-time flows toward the singularity, the current accelerates to terrifying speeds.
Okay, let's unpack this. So gravity isn't a force reaching out and grabbing things. Gravity is just the consequence of the river of space-time flowing downward into this massive canyon.
You've got it. That's it exactly.
And anything caught in the river is just carried along with it.
That is the core of Einstein's general relativity right there.
So the gravity is so immense that it doesn't just bend the fabric of space, it actually breaks time.
Well, yes. Let's look at how this affects time. Time is inextricably linked to the flow of this river. The faster the river of space-time flows, the more the passage of time is stretched out relative to the calm waters far away.
Okay.
So as the current of space-time accelerates toward the black hole, the mechanics of time as we understand them are stretched to their absolute extreme.
Which brings us to the boundary, the waterfall's edge, the event horizon.
The point of no return.
Right. We all know this is the ultimate point of no return, where the gravity is so strong that not even light can escape. But what does that actually mean in the context of our river analogy?
So at the event horizon, the river of space-time is flowing inward at the exact speed of light.
Wait, literally the speed of light.
Literally.
Yeah.
And since nothing can travel faster than the speed of light, it is physically impossible to swim upstream.
Even for light itself.
Exactly. Even light itself, paddling as fast as it possibly can away from the black hole, is just swept backward over the falls.
That is terrifying. But also, if the river of space-time is moving at the speed of light, the visual effects from the outside must be completely absurd.
If they are. They really are.
Let's look at the scenario from the Ziko space stories sources. Say we send an astronaut on a mission. We put them in a ship and send them straight toward the event horizon.
Okay.
And we are safely back here on Earth,
Mm-hmm.
far out in the calm, slow-moving part of the space-time river, just watching them through a massively powerful telescope.
Right. So as the astronaut gets closer and closer to the event horizon, the visual we receive on Earth becomes increasingly bizarre. We don't just see them fall into darkness.
Because the flow of space-time is accelerating around them.
Yes,
Yeah.
stretching time out. So their movements appear to slow down drastically from our perspective. The ship seems to just crawl.
And as they hit the actual boundary, what do we see?
They appear to freeze completely.
Just stop.
They just stop. The light carrying the image of their ship is struggling so hard to climb up the waterfall against that intense gravity that the visual information essentially stalls out. And as they freeze, the image of the ship begins to turn a deep red. It gets redder and redder, frozen in place, until eventually they just fade away into nothingness.
Okay, let me pause you there because that detail is wild.
Yeah.
Why do they turn red?
It's a phenomenon called gravitational redshift.
Gravitational redshift.
Yeah.
Okay.
Light is made up of photons, and photons carry energy. To travel from the edge of a black hole back to our telescope on Earth, those photons have to climb out of an incredibly deep gravitational well.
They have to fight the current of the space-time river.
Exactly. They are swimming upstream, but photons can't slow down. Light always travels at the speed of light no matter what. So how do they expend energy to make the climb?
They lose frequency?
Precisely. They lose energy by stretching out their wavelength.
Hmm.
In the spectrum of visible light, shorter, high-energy wavelengths look blue,
Right.
and longer, lower-energy wavelengths look red. As the light from the astronaut fights the gravity, its wavelength gets stretched longer and longer, shifting the visual color of the ship toward the red end of the spectrum.
That makes so much sense.
Yeah, and eventually, the wavelength stretches so far it moves into infrared, then radio waves, and then they simply vanish from our sight.
Wait, hold on. I need to play skeptic for a second for the listener.
Go for it.
If the people on Earth see the astronaut freeze entirely and turn red, but the astronaut's watch is ticking away at a normal speed, I mean, whose reality is actually correct? Is it just a trick of the light?
What do you mean?
Like, if I just calculate the delay of those stretched out photons reaching my telescope, don't the astronaut and I sync back up in reality? The light taking longer to escape doesn't mean time actually stopped for them, right?
See, that is the trap of classical physics. It is completely intuitive to think it is just a signal delay or some optical illusion.
Yeah, that's what my brain wants to do.
But the staggering truth of the universe is that it is not an illusion. Both realities are correct relative to their positions.
Wait, really? Both?
Both. The rate of time itself has fundamentally decoupled. This is proven. It's called gravitational time dilation. You and the astronaut are both experiencing an entirely real, physically correct flow of time. But those flows are operating at vastly different speeds.
Because time is topographical.
Yes, exactly. You are in a high, flat plane where time moves briskly. They are deep in a steep gravitational valley where the space-time river is rushing violently.
So to the astronaut sitting in the cockpit, their watch ticks away perfectly normally.
Right. 1 second per second. Their heart beats at a normal rate. Everything feels fine.
But if they were to look out their window back at the rest of the universe...
They would see the cosmos seemingly hit fast forward. Stars would be born and die in a blink.
Because their single second stretches out to cover years of our time.
Yes.
That is just mind-blowing. Which means this time slowdown isn't just a cool thought experiment. It has literal, earth-shattering consequences if that astronaut ever decided to turn their ship around and come home.
It really does.
And this leads directly into what I think is the most mind-bending part of Professor Cox's theory, the orbit scenario.
Oh, this is the most powerful application of this physics. What if the astronaut doesn't fall in?
Right. What if they can survive the immense gravitational forces and just, like, orbit just outside the event horizon of a supermassive black hole.
They establish an orbit just millimeters above the event horizon?
To maintain that orbit without falling in, the ship would have to be traveling incredibly fast, right? Like a significant fraction the speed of light just to counteract the gravitational pull.
It would, and that compounds the effect beautifully.
How so?
Well, you have general relativity warping time because of the immense mass of the black hole. And you also have special relativity warping time because of the extreme velocity the ship needs to maintain the orbit.
Ah, so they stack on top of each other.
Exactly. Both effects work together to slow the astronaut's time down to an absolute crawl relative to the rest of the universe.
Okay, so let's do the math on this scenario. The astronaut goes into this extreme orbit. They sit there and watch their clock tick by for exactly 5 minutes.
Just 5 minutes.
5 minutes of monitoring instruments, making notes, maybe drinking a cup of coffee. They fire their thrusters, break away from the gravity well, and navigate back to the calm waters of Earth. What happens?
When they land back on Earth, they don't find the space agency that launched them. They discover that thousands of years have passed back home.
Thousands of years.
Yes.
Just imagine stepping out of your ship into that. You took a 5-minute joyride around a singularity, and the Earth you left is ancient history. Everyone you ever knew, your family, your friends, the entire civilization that built your spaceship, they are long gone.
All of it.
The borders of countries are gone. The languages are unrecognizable. You step out into the entirely unknown, distant future of human civilization.
It is a profound emotional reality to grapple with, absolutely. But it is an absolute mathematical certainty.
That's the crazy part.
If you have a strong enough ship and a massive enough black hole, you can exploit the geometry of space-time to travel forward in time as far as you wish.
Here's where it gets really interesting to me. You aren't just a space explorer anymore. You are a literal time traveler.
You are?
This isn't science fiction movie magic. These are physics-approved shortcuts to the future. Is this why scientists view black holes as actual functional time machines?
Yes, it's exactly why. We always think of time travel requiring a magical machine.
Yeah.
But the universe has already built a naturally occurring time machine using the sheer brute force of gravity.
It just completely redefines humanity's place in the cosmos.
Mm.
We aren't just floating through an empty void. We are navigating a landscape filled with shortcuts to the future.
We are? But there is a catch.
There's always a catch. It is a one-way ticket, right?
Right. You can travel to the future, but general relativity doesn't give you a river that flows backward. You can't return to the past you left.
Because gravity only pulls you in. Which brings us to the ultimate boundary. Hovering around the edge for 5 minutes gives you the keys to the future. But human curiosity is insatiable. We always want to know what happens if we don't turn around.
What actually lies inside the locked door.
Exactly. So let's guide the listener right over the event horizon. We are passing the point of no return, where the river of space-time is now flowing faster than the speed of light. We are plunging straight toward that infinitely dense core, the singularity.
Okay.
What happens to the physics?
Well, taking a serious look at this exact moment is where modern science reaches its ultimate limit.
The breaking point.
Yes. We have mathematical models, specifically solutions to Einstein's field equations, like the Schwarzschild metric, that describe the space-time outside the black hole perfectly.
Right.
But as you cross the event horizon, the mathematics do something astonishing. Inside the singularity, the laws of physics as we know them completely break down. The equations suggest that inside a black hole, space and time physically swap roles.
Space and time swap roles.
Yes.
Let's break down the mechanism of that, because that phrase completely breaks my brain. How does a dimension of distance swap with a dimension of duration?
It's baffling, I know. To understand this, physicists use a concept called light cones.
Okay, light cones.
Right, so imagine that at any given moment, your possible futures exist within a cone of light projecting forward from you.
Like a flashlight beam shining into the future.
Exactly like that. In normal space-time out here on Earth, your light cone points strictly forward in time. You can move around freely in space, left, right, forward, backward, but you are constantly, inevitably pushed forward in time.
Because time pushes us forward whether we like it or not. We can't avoid tomorrow.
Right. Time is the one-way street.
Okay, I follow that.
Now, as you get closer to a black hole, the immense gravity begins to literally tip your light cone over, leaning it toward the massive object.
The rushing river is pulling the cone downstream.
Exactly. When you reach the event horizon, the edge of your light cone is perfectly vertical, One side points straight down into the black hole. And the moment you cross the event horizon, your entire light cone, the entirety of your possible futures, tips over so far that it points inward toward the singularity.
So all of my possible futures are now physically inside the black hole. There's no future that leads out.
Yes, and this is where the mathematical flip happens in the source material. In the equations, the mathematical sign for time becomes positive, and the sign for space becomes negative.
They trade places.
They literally swap. What this means physically is that the singularity at the center is no longer a place in space. It is a point in time.
So what does this all mean? On Earth, we can't stop Tuesday from turning into Wednesday.
Right.
Does this mean that inside a black hole, moving forward in time becomes exactly like moving forward in space? You literally cannot stop yourself from moving toward the center?
I love that translation, and yes, it's absolutely correct. On Earth, time pushes you forward infinitely. Inside a black hole, space takes on that exact property. The singularity is not a destination you are traveling toward in space. It is your inevitable tomorrow.
That is just astonishing.
You cannot stop yourself from moving toward the center, just like you cannot travel backward in time on Earth. Space has become the one-way street.
The singularity becomes a when, not a where. You are falling toward Wednesday.
Yes.
And Wednesday is a point of infinite density where all the known laws of physics completely shatter.
The rules of general relativity dictate that everything inside the event horizon must inevitably crash into the singularity, just as inevitably as time moves forward.
Right.
But this raises the ultimate question of Professor Cox's D-space theories. If physics entirely breaks down and space and time swap roles, what actually happens when you reach Wednesday?
Yeah, what is at the center?
General relativity predicts infinite density, a point where the curvature of space-time becomes infinite, effectively a bottomless pit. But we know general relativity is incomplete because it doesn't account for quantum mechanics.
Because it's too small.
Exactly. When you get down to the unimaginably small scale of the singularity, quantum effects have to take over. And futuristic theoretical physicists suggest some truly astonishing ideas about what that reality looks like.
Because it can't just be a dead end where reality goes to die, right? Nature doesn't usually work like that.
Nature rarely creates true infinities. One of the leading theoretical ideas is that the singularity, this point where time and space fracture, might actually function as a gateway.
A gateway.
The intense compression of space-time might puncture a hole through the fabric of the universe entirely.
Wait. Like an Einstein-Rosen bridge, a wormhole.
Yes, a passage connecting to another region of space-time, or perhaps to another parallel universe entirely.
Oh, wow.
The matter and energy that fall into the black hole, accelerating down that river of space-time, might not be crushed into nothingness. Instead, they might be funneled through this quantum gateway and expelled out the other side.
Like a cosmic exhaust pipe into a new reality.
Basically, yeah.
It is just so incredible to discover that the mechanics of the universe are so much stranger than anything we could invent. I mean, we spend all this time writing sci-fi movies about magical portals.
And the universe has been creating them for billions of years just through the raw, brute force mechanics of gravity and time.
Reality is so much stranger than fiction. The universe doesn't need magic to be astonishing. It just needs physics.
Exactly.
So let's take a breath and look back at the scope of the incredible journey we just took today. We started by busting the grand myth of the cosmic vacuum cleaner.
Right. They aren't just monsters roaming the void looking for planets to eat.
We looked at the topography of the universe and how the massive gravity of a black hole turns space-time into a rushing waterfall that warps the very passage of time.
We examined the visual mechanics at the event horizon, understanding gravitational redshift.
Where photons lose energy fighting the current.
Yes, causing an astronaut to freeze and fade to red from the perspective of Earth, while their own time ticks on normally.
We did the math on a 5-minute orbit around that horizon, realizing that riding the edge of that waterfall could catapult you thousands of years into the future of Earth, turning a space mission into functional time travel.
And finally, we plunged over the edge into a reality where light cones tip over, the math literally flips space and time swap roles, and a physical location becomes your inevitable, inescapable tomorrow. The question we leave you with is one of perspective. When you look up at the night sky now and think about the dark spaces between the stars, how do you weigh the evidence?
Yeah, how do you see those massive gravitational wells?
Are black holes terrifying monsters of destruction ripping apart the fabric of the cosmos? Or are they the keys?
Are they naturally occurring mechanisms for unlocking interstellar time travel and discovering the ultimate hidden architecture of our universe?
We really want you to remember that outer space is far stranger than any movie script.
It fundamentally changes how you view the dark. And before we go, there's one final lingering thought to mull over today. Something to just chew on or explore on your own as you go about your rigid, normal time day.
Oh, I like this one.
We talked about the center of a black hole potentially acting as a gateway, right? A wormhole to a parallel universe where all the matter and light it pulls in is expelled out the other side in a massive explosion of energy.
Yes.
Now, our own universe is absolutely full of massive black holes, and our entire universe began with a massive explosion of energy that we call the Big Bang. So,
Mhm.
could it be that falling into the ultimate destruction of our time, into a singularity, actually serves as the exact doorway to the Big Bang and the birth of a brand new reality?
It is the ultimate cosmic cycle.
Thank you so much for joining us on this thrilling cosmic journey into the unknown deep universe. We hope we made the cosmos feel a little more complex and a lot more magical today. Keep looking up, keep questioning the fabric of reality, and we will see you on the next deep dive.